Welcome to Lecture 24A, entitled Stokes Theorem for 3D. And this is a tooling example where we basically just gain some flexibility of using Stokes Theorem, and that is to calculate the left-hand side and the right-hand side. The material for this video comes from reading Assignment 4, Section 4.2.1. And the objectives are to develop the skills for applying Stokes' theorem to purely geometrical problems. Concepts, conventions, visualization skills include closed contour encloses a surface. In this case, the surface is an open surface, right? So contour basically bounds a surface, but it's an open surface. And the direction of a surface area vector and the direction of the traversal of the contour are related to each other by the right-hand rule. As usual, the second slide is just a review of the slides to follow, so we'll just basically move on. All right, so let's consider a Stokes tooling example. The diagrams you see in this slide, you can basically obtain by just clicking on the link here. And the slider T moves the blue triangle to cover the pyramidal box. So what I've shown here is this cover, which fits over top of this pyramidal shaped box. I just moved it here to make it clear that it's an upper surface. All right, and the problem statement is to evaluate the integral, closed contour integral of f dot r dot dt, where the vector field f is z minus z x squared minus y squared. And the contour that's chosen here, which is TDS, which is equivalent to r dot t dt after parameterization, is taken to be in a counterclockwise direction. This is not a smooth contour, so that means each one of these lines represents a region where you have continuous differentiability. So we need 3 line segments here to define a closed contour. TDS1, TDS2, and TSD3. All right. So C in red consists of 3 line segments, and they bound the plane Z equals 8 minus 4x minus 2y, which would be basically this surface on top of the pyramidal box, and it's in the first octant, oriented according to this particular figure that's shown here. And the vertices of the triangle are 0, 8, which was this point here, 2, 0, 0, which is this point here, and 0, 4, 0, which is this point here. All right, and what I've shown here are basically contour with this surface, which is this flat surface on top of this pyramidal box. But at the same time, that this contour could also be considered as bounding a surface consisting of this triangular section, and this triangular section. This would be 3 discrete surfaces, when stitched together, form an open surface, which is bounded by the same contour shown in red. Now, according to the right-hand rule, the direction of traversal, you use your right hand and the fingers point in the direction traversal, which would be this way around. That means the area vector would be pointing outwards. So for this case, the area is pointing in this direction. In this case, the area vector for each one of these surfaces pointing inwards. So this direction, and this direction. So this is always the first step, is to make sure everything is being labeled. We need to know the direction of the surface area vector, and we need to know the direction of the contours. Now that that's done, we can apply Stokes' theorem to solve the problem, and we're going to do it for 2 specific cases. One in which case we're dealing with the enclosed surface area, which consists of these 3 rectangular regions, and one which just includes this light blue shaded area. All right, so Stokes' theorem is just a closed contour integral of f dot TDS, and in parameterized form, this would be written out in this form, as we call the left-hand side. And the right-hand side would be just the curl of the vector field dot NDS, this representing the differential surface area. We also will need to compute the curl of the vector field. So if we take the curl, we can put this in a determinant form as shown here. First row are the unit vectors, second row the partial derivatives, and third row is the vector field. And basically compute the determinant, and we end up with this being the curl of the vector field F shown here. All right, this is just showing a blow-up now, so this is a little bit more detail, easier to visualize. Consider this 2 simple cases, the light blue shaded area and the 3 triangular segments, which basically form a surface, an open surface bounded by this contour. Okay, so the bluish-gray triangle area is the light blue area projected onto the XY plane. And so here again we have the contour in a counterclockwise direction, the area vector pointing in this direction. Again, right-hand rule. Here we have the same contour, but looking inside the box. Again, these area vectors are pointing in the correct direction according to the right-hand rule. All right, so let's do, for the shaded in light blue, which is the planar area, let's basically do the calculation of the right-hand side. So because the plane equation is given as a function of x and y, that is z is a function of xy, and we need to basically determine what the differential surface area is, it's easiest is to use an explicit representation. And so in this case, the area vector has to be pointing in the z direction, and so this is the appropriate form to take. So z partial x, z partial y, both minus 1 dy dx. And so if you take the equation of the plane, take the partial respect to x and the partial respect to y, times negative, then you'll end up with this vector here, a dy dx. And the direction, as I said, is according to the right-hand convention. The region R, which is the surface over which you're going to integrate, is the triangular region R in the xy plane, which was the darkish grayish blue color. Dark blue, is found by setting z equals 0 in the equation of the oriented plane. And so if we set this equal to 0, that'll give you an equation of y as a function of x, and that can be used then to determine the region. And this is what we've done here. So we have one bound, which will be y equals 0. One bound is 4 minus 2x, and x ranges between 0 and 2. This is the projected area of the plane, z equals 8 minus 4x minus 2y onto the xy plane. All right, so now that we have the region, which basically gives us the integration limits, we also have the surface area vector, and we also have the curl of the vector field. We can now basically do the calculations shown here. So here's the curl of the vector field. Here's the differential surface area. Here are the bounds on the integral. We just perform this integral, and we'll end up with an answer of minus 88 over 3. So in this case, the circulation around the boundary is negative, indicating a net circulation in the counterclockwise direction looking from above. So we just arbitrarily went around in a counterclockwise direction, but we've ended up with a negative circulation, which means the circulation is going actually in the opposite direction, which means its net is in the clockwise direction. Okay, now let's do the 3 discrete planes. Since we're going to basically do the curl over a surface, the surface is not smooth, but consists of 3 triangular segments. And so this double integral is actually the sum of 3 separate integrals in individual surfaces for the 3 different triangular surfaces, S1, S2, and S3. And so we need to basically compute for each one of these cases what is curl of F and what is going to be NDS. So for the y equals 0 plane, we take the curl of F and we set y equal to 0. And so this is the curl of F that we're going to be using as the integrand. For z equals 0, that means we set z equal to 0 in the curl of F. This is the expression we use for the integrand. And for the case x equals 0, set x equals 0 in the curl of F. And this is the expression we use for the integrand. Similarly, at y equals 0, this is the differential area. And so this is the differential area that's pointing in the y direction, which is the correct direction, according to the diagram which we've shown earlier, dx, dz. This is the vector pointing in the z direction for another of the triangular elements, dy, dx. And this is the third, which is in the x direction, dz, dy. Notice that the vector, this basically is the x, this is dz, dy. So it's always going to be, whatever this is, the remaining 2 are the the differential elements. So these are in the correct direction. These we've now computed. And so now the only question is determine the bounds on the integrals. That's for S1, S2, and S3. And so for S1, we'll have 0 is less than equal to y is less than equal to 4 minus 2x, and 0 is less than equal to x is less than equal to 2. And so you can obtain these basically just by looking at the diagrams from the previous page. There's the individual triangles, and you just have to find the bounds. For S of 2, we have these bounds, and for S of 3, we have these bounds. Okay, so just a general note. The differential area can be determined by inspection if the area is very simple. And if that's not the case, you just compute it mathematically. So we more or less have everything ready. We can move to the next step. And so here we just collect the terms and do the integration. So the curl of f dot n s3 ds3, that's the case for y equals 0. We end up with this. For the case z equals 0, this is a different surface area element. Take the dot product, we end up with a 0 value. And for curl of f, evaluate x equals 0 for ns2 ds2, we get 1 minus 2y dz dy. And so we now basically substitute that into the three separate integrals, one here, and one here. The first one, which is the one involving s1, is 0. The involving s2 is 1 minus 2y dz dy, and the one involving s3 is 1 minus 2x dx dz. So these are the two last expressions that you see here. If you do these integrations, again, you'll end up with the answer of minus 88 over 3. So it really didn't matter what surface area we used. We end up with the same result. All right, so now let's calculate the left-hand side of Stokes' theorem. We're basically just looking at the contour, which consists of three separate segments. That is C1, C2, and C3, and I've color-coded them here. We've got C1 in green, we have C2 in orange, and we have C3 in yellow. So we're basically going around the contour in this direction shown here. So we're going to have to parameterize each one of these segments. And so for C1, which is this one here, then with respect to origin, the position vector, we find that the position vector we can choose, that's the simplest one, is the one that's shown here. And t will range from 0 to 2. So that means if you sweep t from 0 to 2, the position vector with respect to the origin will basically be sweeping from this point to this point. All right, so it's going in the correct direction. For the next segment from C3, from C2, the position vector takes on this form. In this case, t is between 0 and 4. And so if you were to sweep from 0t to 4, you would basically be sweeping along this line and again in the correct direction. And finally, for the last portion, which is this contour line segment here, the position for here vector would be t 0, 8 minus 4t, with t varying between 0 and 2. If you sweep this from 0 to 2, you'll basically be sweeping along this line from this point to this point. So your t is always advancing, and it's always going in the correct direction. So you know that this formulation, as far as parameterization is concerned, is perfectly okay. You could have done it differently, but this is the simplest one to consider. Now that we have the position vectors, we can compute the tangent vector. So that means that we can, in parameterized form, this just becomes r dot dt. So if I take derivatives with respect to t, then you'll end up with this expression for contour 1, this expression for contour 2, and this expression for contour 3. At the same time, you have to evaluate what f would be. So the x component of the field vector would be replaced by 2t, 2 minus t. Y component of the field would be replaced by 2t, and the z component would be replaced by 0. So you would end up basically with this expression for the field. For this line segment, we're talking about a different parameterization. In this case, x for the field would be replaced by 0, y would be replaced by 4 minus 2t, and the z component would be replaced by 2t. Finally, for the last contour segment, the field would basically now have x, y, and z being replaced by x equals t, y equals 0, and z equal 8 minus 4t. And so we end up with all of these expressions only being a function of a single variable, and that is the parameterization variable t. So the next step is to take this information, which is the field information and the tangent vector information, and basically compute each one of these individual line integrals. So the dot product between the field and the tangential vector for the first case between 0 and 2, it's between 0 and 2 is 0. Similarly, for the integral for contour C2, in this case, we end up with minus 80 over 3. And for the third segment, we end up with an answer of minus 8 over 3. So the closed contour would be just the sum of the contribution to each one of these line segments. That turns out to be minus 88 over 3. Okay. All right, so let's consider another problem and its solution. And the problem statement here is that we're expected to compute the line integral, closed line integral, this basically being the x component of the field, this being the y component of the field, and this being the z component of the field. But this is in explicit form. All right, C is given, and it's the curve R of t in parameterized form, sine t, cos t, sine 2t, and t is evaluated from 0 to 2 pi. So this essentially means you're making one full closed loop. And it lies on the surface defined by z equals 2xy. How do I know that? Well, if I substitute in for x, that is sine t, and substitute for y, cos t, I end up with z is equal to 2 sine t cos t. But that's nothing more than sine 2t. So this actually is this particular line does lie on the surface defined by z equals 2xy. All right, just two observations. First of all, that any form of closed line integral can be associated with Stokes' theorem. And we have a line integral. And any surface bounded by a closed contour can be associated with Stokes' theorem. So we can look at it from both perspectives, either from a line integral or from a surface integral point of view, and they're related to each other through Stokes' theorem. So we're going to apply Stokes' theorem, which is in this form. This is basically the line integral on the left-hand side, and this is the surface integral on the right-hand side. The question you might ask for this particular problem is it easier to compute the right-hand side or left-hand side of Stokes' theorem? Which is easier? All right, this basically is a line integral form, so you can write its equivalent also in terms of a surface integral if you wish. All right, but the first step is to determine the orientation of the curve, because without that, we don't know what the direction of NDS needs to be. And so since it's a given, we can basically show that the position vector being given turns out that this orientation is clockwise. So as t advances from 0 to 2 pi, you're actually traversing this contour in a clockwise direction. And therefore, using the right-hand rule, you basically would have the fingers pointing in the direction of the traversal of the contour, and the thumb would point in the direction of the surface area. And so I've shown here two surface areas, one of them being the actual surface area, which is defined by z equals 2xy, and a projection of that surface area. In either case, basically, the surface area for this particular surface z equals 2xy would be pointing in this direction when we're talking about a traversal around this boundary, which is in a clockwise direction. All right, so let's do the calculation. If we were to write out the left-hand side of Stokes' theorem, okay, which would be this part here, you'd start with dx equals dx dt dt, dy equals dy dt dt, and dz equals dz dt dt. And recall from a previous lecture that TDS is just dr dt dt. This is the vector, the position vector. All right, and this would be just like writing this out in full form, dx dt, dy dt, dz dt. All right, and this we would call r dot dt. But if you multiply through, this is also equivalent to dx dy dz. So this is the explicit representation. This is a parameterized representation. So that means we could write this expression that we were given as basically this in explicit form times, or at least dot product with dx dy dz. And so from this it's clear that the f vector is y plus sine x, z squared plus cos y, x cubed. All right, so this expression that we're looking at looks messy. All right, so right away we're going to make the call. I don't think I want to go that way. So instead we're going to explore the right-hand side of Stokes' theorem for calculation process. So what do we need to do? We're going to have to determine what the curl is. We're going to have to determine the orientation of the surface area vector. We also determine what surface area to use, because it's really up to us to choose the surface area. And so there are a number of options here. Two things have to calculate, but we also have to detect what the surface shape should look like. All right, so next is to basically compute the right-hand side of Stokes' theorem, which is the portion shaded in green that you see here. So first of all, if we look down onto the xy plane, that's down in this direction, the contour is traversed in a clockwise direction. Therefore, the right-hand convention would stipulate that the area vector NDS has a z component which points in the minus z hat direction. That's pointing downwards. So this is basically the arrow that you see here. It's pointing downwards from this curved surface. The surface z of fxy is 2xy is given in explicit form. So the surface area vector pointing downwards can be expressed as follows. So again, is z partial x, z partial y minus 1. This indicates downwards, so this is in the correct direction according to the right-hand convention. So the vector pointing normal to the surface and downwards therefore becomes 2y 2x minus 1. So z partial x applied to the function 2xy would give you 2y, z partial y would give you 2x, hence the first two terms shown here. And the curl of the vector field basically is minus 2z minus 3x squared minus 1. However, we're evaluating this on the surface, and so that would be when z is equals to 2xy, and hence the calculation of the curl will be the situation where z equals 2xy, which means this first term becomes minus 4xy. The y component and the z component are unaffected because there's no z component showing up in this expression. All right, now that we have done the computations for the curl of the vector and the surface area of the vector, then from the previous slide we can basically make the substitutions for the curl of f, which is evaluated, these are for the field evaluated on the surface. This is an explicit form, and this is the surface area vector that's shown here. And so we take the dot product, and the resultant of that is a scalar function, which is shown here. And now we have to integrate over the region. Well, the integration region is basically bound for the region, or just the projection of the surface, which is this reddish area, onto the xy plane, and that turns out to be basically the circle that you see here. So how is that obtained? Well, the bounds of the region of integration are determined by the projection of the contour onto the xy plane, and the bounds can be easily determined by taking the original position vector and setting the z component of the vector to 0, which more or less is a projection, which implies that the position vector has the following form. And if you basically take this and represent it in 2D, this is just sine t cos t, and the integration bounds for this are from t0 to z 2 pi. This is just a definition of a circle of radius r, of radius 1 on the xy plane. Again, this is what's shown shaded in gray, and therefore, if we were to describe the bounds of this region in Cartesian coordinates, since this is already stipulated in terms of Cartesian coordinates, then for y we would have a half circle and a lower circle, one circle, half circle above, for greater than y, and one for less than y. So these are the bounds on y that you see. Circle is radius 1, so square root 1 minus x squared for the upper bound, and minus square root 1 minus x squared for the lower bound. And x will range from minus 1 to 1. So these are the bounds that will basically be put into this double integral, which is now double integral on the xy plane. All right, so now we basically just put it together. Here are the bounds. Here's the resultant of the dot product, and so now we integrate this. Of course, we look at it and say there might be an easier way to integrate it. This looks like a problem in which we could use polar coordinates. Recall, in polar coordinates, x is r cos theta, and y equals r sine theta, and dy dx becomes r dr d theta. So we just transform the integral so that this now just becomes the radius from 0 to 1, and we go once around the circle from 0 to 2 pi. And we make the substitution for x from here, the substitution for y from here, put it together, and we end up with this expression. After integrating with respect to r, we end up with this expression, and the last step is to integrate with respect to theta. So finally, we end up with an answer of pi. If you work through this, you'll have to use some trigonometric identities to get into a form which is suitable, but the final answer in this case is pi. That concludes Lecture 24A. Thank you for listening.